Okay, good morning, everybody. This is Professor Andrea Ghez from UCLA, the University of California at Los Angeles. And it was just announced this morning that she's one of the recipients of the 2020 Nobel Prize in Physics. As it happens, we were about to talk about her work today anyway. What she got the Nobel Prize for, she shared with other people, is in discovering the black hole at the center of our own galaxy. A black hole is a very, very massive object that's so massive that even light can't escape from it, so you can't actually see it, so discovering it is actually hard. And we'll talk a little bit about how she did that, because we are in a position to understand that after we do a few things at the beginning of today's lecture. So that's a piece of our goal for today. So let's review where we were at the end of our last lecture. And the last lecture introduced some kind of sophisticated ideas that take a minute to wrap your head around. So we need a few minutes to work with them. So we've been working with the momentum principle in the form, the rate of change of momentum is equal to the net force acting on a system at any instant. So this is an instantaneous version of the momentum principle. Yes, Roger Penrose and Reinhard Getzel also got the Nobel Prize. Penrose's work on black holes was theoretical. What Penrose did was to show clearly that in the real world, the consequences of Einstein's theory of general relativity really did predict the existence of black holes, which were kind of suggested by that theory, but nobody knew whether they'd be real or not. And what both Andrea Ghez and Reinhard Genzel did was actually, by very difficult observations, prove the existence of the black hole at the center of our own galaxy and actually determine its mass. And we'll see how they did that. And we saw that we can write the net force acting on an object at an now notice that this, let's go back to the momentum principle for a minute. Notice that although the rate of change of momentum with respect to time is numerically equal to the net force acting on a system, these are not the same thing. These are different things. So the force we can calculate if we know force laws. So for example, if it's a gravitational force, we can calculate that the rate of change of momentum we get from observing momentum at different times and calculating delta p and then dividing by delta t and taking these observation times closer and closer together so we can actually get a value that for dp dt. So they're really, it doesn't say they're the same thing. It says there are two quantities which are equal. And in fact, there's sort of a cause-effect relationship. The net force is, this is the interaction, that's the cause. And this is the effect that we observe, a change in the motion of a system. So this is a causal equation. It doesn't mean things are the same. We found we could write the net force usefully as having two components, a component that's perpendicular to the momentum of a system and a component that is parallel to the momentum of a system. And these two components did different things. This one turns the momentum, and this changes the magnitude, speeds up, slows down. We also found that by using calculus that we actually, if we just use the product rule, we could write the rate of change of momentum of a system as the sum of two things also. A component of this that is perpendicular to the current momentum, and a component of this that is parallel to the momentum. And this will turn out to be useful because sometimes even if we don't know one, we can figure out the other, and that tells us something about force components, because this equality tells us that F net perpendicular is equal to the perpendicular component of the rate of change of dp dt, and that the parallel component of the net force, and when I say perpendicular and parallel, I always mean perpendicular to the momentum of the system at that instant, or parallel to the momentum of the system at that instant. So the component that's parallel to the momentum is equal to the parallel component of the rate of change of momentum. Now this all sounds a bit abstract, but it's a very concrete thing. And so I thought maybe it would actually help to just calculate this. So let's consider an elliptical orbit. So you've written a program in which a spacecraft orbited the Earth, and if you explored it all, you found that most orbits are elliptical, and a circular orbit is a super special case with very precise initial conditions. So let's consider a situation where we've got one of these elliptical orbits. We've got something here, let's take our spacecraft and the Earth, for example. So here's the Earth, and at a certain, and what we're doing is iteratively applying the momentum principle, knowing the force to calculate the momentum. And what I did is take a program like that and just put in some code to print out the momentum at different times. And so when I clicked, so what I got was a value of momentum just before the spacecraft reached the midpoint here, and another value just after. And I thought it would be interesting just to use these two values to calculate an approximate value of the rate of change of momentum when the spacecraft is at the midpoint in between those two times. So we want to find delta P over delta T here. And so time one in the orbit turned out to be 2.17 times 10 to the 4 seconds past whenever I started it. And the momentum of the spacecraft at that instant was 4.00 times 10 to the 4th, 4.89 times 10 to the 5th, 0 kilogram meters per second. And at T2, the time was 12.26 times 10 to the 4 seconds, and the momentum was a vector minus 5.86 times 10 to the 4th, 4.88 times 10 to the 5th, 0 kilogram meters per second. And so to get delta P over delta T, we just take, and of course I did this in GlowScript, P2 minus P1 divided by T2 minus T1. And what I got was a value of minus 0.98 minus 9.16 times 10 to the minus third, 0 kilogram meters per second, or kilogram meters per second squared. And that, so if we try to draw this on the diagram, we find that the x component here is much bigger than the y component. And in fact, the y component is actually going to be too small to draw very much here. So we have I didn't bracket this particular location perfectly, but basically we have a delta p over delta t here, an approximation to dp dt. That's almost entirely perpendicular to the momentum at this point. So this is dp dt perpendicular just because of our axis system. And this is dp dt, that's the parallel part there. And so this should be equal numerically to the net force acting on the object at the moment, and it sure looks like it's the right direction, doesn't it? Because the net force is, in our model, it was a simple model, the only thing exerting a force on the spacecraft was the Earth. So that looks like it's the right direction, and we could, if we knew exactly the position at this midpoint, we could calculate the force and see if it actually came out to be equal. So it's a very concrete thing. And the only reason that the x component is the perpendicular component and the y component is the parallel component is because we took an instant here where the momentum was almost entirely, or ideally would have been entirely, in the plus y direction. So that's not, so there's nothing really magical about this. It's pretty straightforward. So the game we want to play in solving problems is to say there are situations where we can see the motion of something. So from the motion of something, we can figure out the rate of change of momentum. So we observe this, we deduce this, and what that lets us do is deduce the net force acting on something, even if we can't calculate it. And even if we can't deduce both pieces of dp dt, if we can get the perpendicular piece of dp dt from the curvature of the orbit, then we should be able to get the perpendicular piece of the net force. Now, it turns out that I'm switching to glow script so I can show you something here. That in any orbit, and this is I think it's a spacecraft in the Earth, but it could be the Earth and the Sun, or it's a planet and the Sun. And so here's the magenta trail is the actual path of the object. But at any moment in this curving orbit, we can draw a circle that's tangent to the path at the location of the object, and that's what the green circle is. And what that green circle gives us is the instantaneous radius of curvature of this orbit. And the instantaneous radius of curvature of the orbit is the thing that that allows us to deduce the perpendicular component of dp dt. This this circle is sometimes called the kissing circle because it just kisses the orbit. Now, what do you think the blue and red arrows are here that are attached to our orbiting body? Okay, so one person says that they're the perpendicular and parallel components of the force. And another person says they're related to momentum. They're not the momentum because the momentum is in fact tangent to the magenta line, right? So what these are is indeed, in this case, the rate of change. The red arrow is dp dt. It's the rate of change of the momentum. And yes, it's in exactly the same direction as the net force acting on the object, and it has exactly the same magnitude. And the blue arrow pointing toward the center of the green circle is the component of dp dt perpendicular to the momentum. And the blue arrow pointing along the trajectory is the component of dp dt parallel to the momentum. So let's wait till they get a little bit bigger and then stop this so we can analyze it here. Okay, they're big enough to see, so let's stop this thing and look at it. So the red arrow here is dp dt. It's the rate of change of the momentum. Now notice that it's not in the direction of the momentum. It's changing in a direction that is the same as the direction of the net force acting on the object. In this particular situation here, we've stopped it at the top. The orbiting body is speeding up. It's going faster because it's getting pulled toward, let's say it's a planet, it's getting pulled toward this star. So the parallel component of the PDT is actually in the direction of momentum because it's increasing its magnitude. And the perpendicular component is in the direction that it's turning. So you apply an impulse down and that turns the momentum and keeps it curving the right way. And you can see that dPdt perpendicular is actually pointing toward the center of this green circle, this kissing circle. So at any point, if we start this running again and stop it, we can see that the perpendicular component of dPdt is always pointing toward the center of the kissing circle. So if we know the instantaneous radius of curvature of the orbit at this moment, which we would know if we knew the radius of the kissing circle, we could draw the kissing circle and figure that out, then we could actually, it turns out we can actually calculate exactly like the guy who was bad at golf, hitting the bowling ball toward the center of the circle to make it turn in a circle. So it's exactly like that. And now here, interestingly, if you thought this was part of momentum, think again, because now the comet, the planet is headed down and to the right. So it's headed away, getting farther from the star. The component of dPdt that turns the momentum, the perpendicular component, is large. It goes right through the center of that green kissing circle, and the green circle is now small because there's a tight curvature in the orbit. The component of dp dt that's parallel to momentum is actually in the opposite direction from momentum, right? Because the momentum is counterclockwise, and that's pointing clockwise. So if we can figure out the relationship of the perpendicular component of dp dt to the ratio of this kissing circle, the radius of curvature of the orbit, then we should be able to solve lots of interesting problems that way, or some interesting problems that way. So what we're going to show, to show is that the perpendicular component of dp dt, the absolute value of this, magnitude of this, is actually going to be equal to the magnitude of the momentum times the speed, the magnitude of velocity over this is the instantaneous radius of curvature. So the radius of that green kissing circle. Now, if the orbit happens to be a circle, then the kissing circle is the orbit. It's the same thing, right? If it's not, then, as you saw, it's a circle that's tangent to the orbit at that location. And so this is, and of course we can rewrite this. Well, this is actually equal to gamma mv, and here I'm writing a v without a decoration to show that I mean the magnitude of the velocity or the speed. So that's the magnitude of p times the speed over r, or gamma mv squared over r. And if we're talking about speeds slow compared to the speed of light, which we often will be, then if gamma is approximately 1, then the perpendicular component of dp dt, the magnitude, is going to be equal to mv squared over r. The proof is geometric, and I'll sketch it for you here. It's actually in the textbook. If we consider something moving in a circle, we'll take. I'm gonna take locations that are actually fairly far apart, just so I can draw them. But we're going to eventually want to take them close together as the limit to get an instantaneous thing. So let's consider an object here in this orbit, and it's going counterclockwise. So its momentum is here at that instant. And now we want to find dp dt. So what we're going to do is consider its momentum a certain time after that that time, and we're going to take its momentum an equal time interval before that time, so our time interval brackets the instant of interest. And we're going to draw a triangle from the center of this circle that involves these two locations, and this is some angle theta. Now the arc length, so how far did this thing go? So this arc length distance is just equal to the speed times the time in between these two observations. And okay. Now, because the momentum is so, if we wanted to calculate delta P, so to get delta P here, we draw P initial and P final tail to tail. And then we subtract P final minus P initial, so we draw from initial to final. And so we get a delta P in that direction. So we know that our delta P at that instant, the PDT, is going to be pointing that way. Now, because the momentum is actually perpendicular to the radius in both of these situations here, as the momentum rotates, as the object travels through this angle theta, you can say that the momentum vector rotated from P initial, it rotated to P final through this angle theta. And therefore, that this is the same angle theta because as this angle. If we draw this triangle, which is R, R, and V delta T, and I know that the chord isn't exactly the same as the arc length, but as we bring these things closer and closer together, the chord approaches the arc length, which is the argument we're making here. So that we actually have two similar triangles. So here's one, and let me redraw this at the same orientation so it looks more similar. Here's R, R, and V delta T, and this angle is theta. So because these are similar triangles, we have the ratio of, so similar. So we have the ratio of delta P over the magnitude of P here is equal to V delta T over R. We can actually think of this, though, as not just momentum, but the unit vectors. So we have, this is actually, we could write this, we could have drawn P hat initial and a P hat final. So this could be the rate of change of, and we could draw, so we could draw our triangle as P hat final, P hat initial, delta P hat. So we can write it as delta P hat over the absolute value, the magnitude of that over the magnitude of P hat, which is 1, is equal to B delta T over R. And by just rearranging it, we're going to get a delta P hat over a delta T. So, and this is equal to 1 here, is equal to V over R. So what we've come up with from this geometric argument is that and as we bring these closer together, we get the instantaneous values. So we get that the absolute value of the rate of change of P hat is equal to the speed over the radius. And we remember that dp dt perpendicular, that thing, was equal to the magnitude of p times the rate of change of the direction of p. So we get that dp dt perpendicular in this circle is equal to the magnitude of p times v over r, or if v is much less than c, we get an mv squared over r. So that's the argument. Now, when do we know that? So this gives us a way of solving for of finding the perpendicular component of dp dt just from motion, even if we don't know the force. So we can find dp dt perpendicular from motion, even if we don't know the force. So when do we know the radius of the kissing circle? Well, the easy situation is when things are moving in a circle, right? So easy situation. Circular motion. And so what are we going to do? Well, we're going to use the momentum principle. So the momentum principle so here's our thing moving in a circle. It's not a great circle, but it'll do. And it's moving around, let's say it's a gravitational force, so it's an orbit like what we've been working with. So here's the force, here's momentum. And from the momentum principle, we know that dp dt perpendicular now, the magnitude of that is equal to the perpendicular component of the net force. And in this case, if it's moving at constant speed, that's all there is. If it's speeding up or slowing down, we still have to do some work to deal with the parallel component. But we now have an expression for this. We have mv squared over r is equal to the magnitude of the gravitational force. So what does this m mean? This is the mass of our little object here. So let's say this is a planet, and that's a star. And so we'll say the mass of the planet times v squared is the magnitude of the gravitational force, which is the mass of the star times the mass of the planet over r squared, and there's an r hat in here. But of course, if we take the magnitude, we're going to get the mass of the planet. V squared over r is just going to be g, mass of the star, mass of the planet, over r squared. And we can simplify this a little bit. It's kind of interesting. So we can cancel out things that appear on both sides. So the mass of the planet turns out to appear on both sides. And so we can divide through by the mass of the planet, and that goes away. We've got an r in the denominator on both sides. So if we multiply through by r, we're going to get v squared equals is g times the mass of the star over r. And there's several interesting things about this equation. The first is what's not in the equation. So what happened to the mass of the planet? It's gone, right? So it's independent of the mass of the planet. It only depends on the mass of the star. Furthermore, it gives us a relationship between speed and radius. And so one thing we can do is solve for speed as a function of radius. So we could say, if we wanted to know the speed, we could say the speed of an orbiting object is the square root of g mass of the star over r. And that says that for a given radius, there's only one possible speed. So a satellite orbiting the Earth, for example, depending on how high it is above the center of the Earth, can only have one speed. If you want it to go around faster, let's see. If you want it to go around faster, should it be closer or farther away? Okay, so if r gets big, here you're dividing by a big number and v gets small. So bigger r, smaller v, smaller r, bigger v. And there are various other things we can do with this relationship. So that brings us to what Andrea Ghez did in finding a black hole. At the center of our own galaxy. So it's actually pretty tough to see things at the center of our galaxy because there's a lot of gas in the way. And so optical telescopes can't actually see the center of our galaxy because the gas scatters all the light coming from the stars. So what she did is look at, she and her colleagues did, is look at this, at a star orbiting near the center of the Milky Way galaxy with infrared telescopes. So infrared light can't be detected by the human eye. You actually can detect infrared radiation with your skin because it's what you feel as heat. If you put your hand next to something that's hot but don't even touch it, you can still feel the infrared radiation coming off of that hot object and touching your hand and getting to your hand. So you can detect infrared radiation that way, but we have infrared telescopes. And it turned out infrared radiation from these stars orbiting near the center of the Milky Way it was possible to detect it. And an interesting thing about these stars is they were going really, really fast. So it takes our sun about 230 million years to make one orbit around the center of our galaxy. These things were orbiting in a decade or sometimes less than a decade. So they were going really, really, really fast. And what she did was and so here are some of her observations. This is actually a homework problem in the textbook. Here's some of her observations from 1995 through 2012. She now has more observations, of course, of a particular star making an orbit near the center of the galaxy. Now, detailed analysis, we'd have to be a little more precise than what we're going to do here because you can see that actually the speed isn't constant. So if this is a measurement, these are measurements made every year. And you can see that the ones in the 90s are much closer together, and the ones in the 2000s are farther apart, so obviously it's speeded up. So it isn't clear that we're looking at the, first of all, it's not clear that we're looking directly at the orbit. We might actually be looking at it edge on. And second, it may not, it may really not be at quite a constant speed, but nonetheless, we have a chance of estimating the mass of the object that it's orbiting just from the observations of its motion. So here's a case where we're going to use the rate of change of momentum. What she did was she used the rate of change of momentum to deduce the net force acting on the star, which then allowed her to deduce the mass of the whatever it is of the thing, the black hole at the center. So we can actually use an estimate to get there. So remember, we got this equation, which was, we got v squared is g mass of the whatever, in this case it would be the black hole, divided by the radius of the orbit. And so we could solve for the mass of the black hole if we had v squared r divided by g, should give us the mass of the black hole. Just from these observations, we know the radius of the orbit. It's about 3 times 10 to the 14th meters. We know the gravitational constant, so we have to estimate the speed of the star from this, from these observations. And so one thing we can do to estimate the speed of the star is to say, well, if we just get a known distance and divide by a time, we can get the speed. So estimate v by distance over time. So an easy thing to do is to say, how long does it take to get a quarter of the way around the circle? So from 2001 to 2008, it went about a quarter of the way around the circle. So that would mean that the distance was approximately, well, it's gone through an angle of what? Pi over 2 radians times the radius, that'll give us the arc length of that it swept out, right? And this is 7 years. So we're going to have pi over 2 times 2.9 times 10 to the 14 meters divided by 7 years times 365 days per year times 24 hours per day times 60 minutes per hour times 60 seconds per minute, which should give us a speed. And that comes out to, well, let's just do it. So let's use our friendly local glow script as a calculator. So black hole, we'll call this black hole, I guess. And so we have distance equals pi over 2 times r. What's r? We better we better define R. R was, what did I say it was? 2.9 times 10 to the 14th meters. And delta T is equal to 8 years times 365 days per year times 24 hours per day times 60 minutes per hour times 60 seconds per minute. And V is equal to D over delta T. So let's print the speed. So again, it's going about 2 times 10 to the 6 meters per second, which is, yeah, you're right, it is 7 years. Thank you. 7 years. 7 years. Even faster, 2 times 10 to the 6th meters per second. Thank you, Gabriella. Okay. And so now we can use our equation here. So to avoid switching back, I'm going to type out what we had. So we had V squared, I'm typing it as a comment, V squared. So we had, what was it? We have mv squared over r is equal to gm. Oh, that's a mv squared. That's the mass of the star over r is equal to g times the mass of the black hole times the mass of the star over r squared. And what we want to, so the little m's drop out, so we have v squared divided by r is equal to gm over r squared, and we can get rid of that. So v squared is equal to gm over r. We want to solve for m. M is going to be equal to v squared times r divided by g, right? So mass is equal to v squared times r divided by g, and we better define g. So let's put it up here with our constants. G is equal to 6.7 times 10 to the minus 11 Newton meters squared per kilogram squared. And so we should have solved for m here, so let's print it. We get a mass for this thing of about approximately 2 times 10 to the 37th kilograms. Now for comparison, the mass of our sun is equal to, I think, about 2 times 10 to the 30th kilograms. So let's print the ratio m over m sun. So it's about 10 to the 7th solar masses. So it's roughly 10 million solar masses. So we'll copy that result and paste it in here into our OneNote notebook. So that is a very massive object. It's about 10 million solar masses. So we get, so let's just write down here what we did. So we have a record of it. We used that equation. We estimated V, and we got the mass of the black hole is approximately 2 times 10 to the 37 kilograms, which is approximately 1 times 10 to the 7 solar masses. So about 10 million times as massive as our sun. This is something that's really massive, isn't it? And black holes are very, very, very massive. Black holes are, as we understand it, formed by just by gravitational accretion. Something that may start out as a star, a massive star, gravitationally attracts matter around it. So it grows and grows and grows. But as it gets massive, the internal gravitational forces are huge. So the star itself gets compressed because the mass at the inside of the star is big enough that it attracts the mass on the outside of the star toward it. So it gets compressed to a very small region. And according to the general theory of relativity, so much mass accumulates in this black hole that the gravitational effects are so big that even light can't get out. So even though there is matter it's inside, no light escapes to tell us that it's there. And the only way we can see it's there is by its effect on things around us. So this was a brilliant piece of work, and you can see how long it took. I mean, it took many years of painstaking observations and a lot of very careful work to account for the distortion of the infrared radiation from this star by the gas at the center of the Milky Way galaxy, and also the distortion of those images by the Earth's atmosphere. So there was a lot of very careful work to correct their observations for that. And it's because they needed fairly precise measurements of the location of the star they were watching in order to get this, to be able to draw this conclusion. And I think I believe, you can check this because I'm sure now it's all over the news since she just got the Nobel Prize this morning. But I think the answer came out to closer to 4 times 10 to the 6 solar masses or something like that. So about 4 million solar masses, not 10 million, but I could be wrong. I haven't. Light does not have mass, Alexander. It's a good question. So a photon, which is a particle of light, which we'll be talking about actually, starting in chapter 6, has no mass per se. It has no mass, no rest mass. But because it's moving, it has energy, and Einstein showed that energy is equivalent to mass, so that something that's moving actually can be affected by gravitation. Something that has energy can be affected by gravitation. So do black holes ever die, or do they just keep absorbing things forever? I think the answer is we don't know. There's a lot of mysteries surrounding black holes, and it's an extremely active area of research. If you followed or even just heard of the results of the LIGO observatory, the Large Interferometric Gravitational Observatory, the first it was built originally in the United States. There's one piece in Washington State and one piece in Louisiana. And it detects actually a different kind of, not electromagnetic radiation, but gravitational radiation coming from masses whose momentum is changing. And they actually have detected black holes, a binary combination of black holes orbiting each other and spiraling in and merging to become one black hole. So they certainly, they can eat each other and grow more massive. And so the phenomena we see associated with black holes affecting objects around them have to do with actually growing in mass. But it's also possible, I think, that a tiny black hole, an infinitesimal black hole, which doesn't have enough mass to keep absorbing mass and getting bigger and bigger, can eventually die because what the famous physicist Stephen Hawking showed before his death was a thing called Hawking radiation was possible. There was a little bit of a way for these black holes to lose a little bit of energy. And as they lose energy, then they become less massive and eventually they die. So there's a lot more for us to talk about when we get to talking about energy, which is chapter 6, actually. So Melinda asked, is there a temperature that doesn't give off light? And I think you may be referring to ordinary. So in ordinary matter, even as it approaches absolute zero, it turns out that there's a certain amount of motion of the atoms in matter that never stops. And so even very, 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 very cold matter at temperatures approaching absolute zero, still actually is capable of, well, it isn't going to, it is, if it's in its lowest state, which we call the ground state, then it can't emit energy, but it can absorb energy and then re-emit it. So if everything's in its ground state, you won't see it giving off radiation. And that's chapter 8. So we have good stuff to talk about here. I will post a link to a little video of stars orbiting the black hole, but I'm not going to show you the movie now, but I'll just put it in here as a reminder to. It's just a YouTube video. So you can actually check that out. So there are lots of situations in which this relationship, this dp dt perpendicular is equal to PV over R relationship is useful. And one of them is, in fact, in analyzing motion like a pendulum or like a Spiderman swinging on a web. So if we have something that travels through what's basically a circular arc, we can draw conclusions about the net force acting on this person just from observing their motion. And that's interesting because we don't have a way from first principles to calculate the force that something like a vine or a wire exerts on something. It depends on how much it stretches, right? What its Young's modulus is, and we don't know from first principles what that's going to be. Okay, so we have two questions here that are good questions. The first question is, does that mean that objects traveling in the same orbit, so satellites, Earth satellites, traveling at a radius of 300 kilometers from the Earth, whatever, would they always be traveling with the same speed regardless of their mass? Yes, that is what it means. That's an interesting result, isn't it? But we found here that so in this equation that we derived here from the momentum principle, we found that the speed in something in an orbit, a circular orbit, only depended on the mass of the thing it was orbiting and the radius. So if they're the same radius, they're traveling at the same speed. And that's an interesting conclusion. We have a question, how, if we know F perpendicular, how do we get F parallel? And so the answer is we actually probably can get it here from looking at the speed, if we look at changes of speed. So, for example, we could estimate F parallel in this situation by getting some sort of an average speed 1 here. And then, so we use, say, a 3-year average to get something like an average speed here. And then up here where it's going a little bit faster, we get another average speed. And if we look at remember that the parallel component of dp dt reflects changes in magnitude of momentum. And so if we know how much it's speeding up, and that's reflected by how much it's speeding up, right? Its mass isn't changing, so a change in magnitude of momentum is related to how much its speed is increasing. So if we actually determine the rate at which speed was increasing, then we could determine the parallel component of dp dt, and then so we could get it. So dp dt perpendicular gives us the magnitude of the perpendicular component of the force, and dp dt parallel, let's make that a little clearer, parallel gives us the magnitude of the parallel component of the force. Now, I want to talk about Spiderman swinging on a vine briefly, because it allows us to do something interesting with this idea. So here's the scenario. Spiderman's in some Spider-Verse or other. Spider-Man is out of web fluid, and he has to cross a river. So he's gonna swing from. He finds a vine that he thinks he can swing across the river on. And so if Spider-Man is not dumb, so he decides to hang from the vine to see if it'll hold his weight before he tries this. So he just hangs from the vine. And this is Spider-Man. And we find that that it's fine, right? So if we do the analysis, we have a force down due to the earth. We have a force up due to the vine, and they're equal and opposite. So let's say Spider-Man's mass is 100 kilograms. So we have dp dt is 0 in this case, because he's just hanging. So that's going to be equal to the net force acting on Spider-Man, and that's equal to F vine plus F earth. And if we want to just take magnitudes here, notice we have to add these before we take the magnitudes, right? That's going to be 0. So F vine is equal to the magnitude of force by the earth, which is 9.8 newtons per kilogram times 100 kilograms, or 980 newtons. So, okay, the vine can exert a force of 980 newtons. But now the question is, so This is a static situation. In a dynamic situation, Spiderman is swinging, so he's, let's say, he's swinging from the vine. He started here. He's now here. He's going that way, and he wants to get to there where he can let go of the vine. So is there a chance, though, that the vine's going to break? Did he do the right test? Because the vine now has to do two things. It not only has to support his weight, it's got to turn his momentum. And so the question is, does the vine have to exert a greater force in this situation? So let's think about the direction of dp/dt. Let's do the analysis here, because dp/dt is not zero, right? Because here momentum was zero, and when he gets to this other end, momentum is zero, but he's speeding up here. He's slowing down here. Well, at this instant, this is an easy instant to analyze in some ways, because we have the force of the Earth is still down, and the force of the vine is still up. But we now know that dp/dt is not zero. And so let's think about the direction of dp/dt. So at this instant, we had a little bit before that, we had a momentum, initial momentum that way. A little bit after that, we're going to have a final momentum that way. So we have a P final minus P initial shows us that dp/dt is actually up, and therefore dp/dt is non-zero. And it actually looks like at this particular instant, it's only the perpendicular component that matters. Okay. So at this very instant, it's going as fast as it can, but it's neither speeding up nor slowing down at this instant. So now we're going to find that we can analyze this. dp/dt perpendicular is going to be equal to mv squared over r. And let's see what that tells us. So let's say that Spiderman's mass is 100 kilograms. We already said that. Let's say that at this instant, he's going 13 meters per second, a little bit faster than a sprinter can sprint the 100-meter dash. And the length of the vine is 5 meters. So we get 100 kilograms times 13 meters per second squared divided by 5 meters, which is equal to 3380 newtons, actually. And the net force up here is we have a force of 980 newtons down, but the force that the vine is actually having to exert is not only that, but it's got to be enough so that the net force comes out to that. So it turns out the force by the vine is going to be equal to 3380 newtons plus 980 newtons. This is to turn his momentum, and this is to support weight. And so it's 4360 newtons. It's a huge force required to turn his momentum, and there is a chance the vine's going to break and embarrassingly dump him into the river. So Spiderman may fall into the river. So this is another example of applying the momentum principle, where we have dp dt equals f net, but dp dt is not zero. Now it's a very, there's something hardwired in our brains that wants us to say, in every circumstance, all the forces acting on an object add up to zero. But it's often not true, and so we have to, even if we have that reaction, which seems to be kind of hardwired, we have to say, but wait, I have to check this with physics. Is it really zero or not? And here, since we see the direction of his momentum changing, we know that dp dt is actually not going to be zero. So the net force acting on him at the bottom of this swing is actually not zero. So that's another example of applying this thing that we worked out, this equation for the perpendicular component of dp dt in curving motion. And here, of course, we're assuming that the vine didn't stretch very much, so the length of the vine stays 5 meters. And that's probably a reasonable assumption, right? We saw with wires, they stretched only a tiny amount. Now, maybe the vine does stretch a little more than that when it has to exert such a big force. But chances are that it may break. A thing that we haven't done in this chapter is what's called statics, and it's the section at the beginning of the chapter here. And it involves situations where dp dt is zero. And there are lots of situations that you can draw pictures of. So here's a box, and you've got a couple of string. You've got a string on a spring connected to a block, and you've got all these forces acting on the block, and you know that dp dt is zero, so the net force is zero. And the kind of problem that's often given is to say, okay, we know the net force is zero, and if we can certainly calculate, if we know the mass of something, then we can calculate this gravitational force. And we can often use the geometry of the situation to deduce things about the other forces. So the way this works is you say, well, we can resolve the force by this string here into an upward component, and so that's a y component, and that's an x component, and just from the angle here. And so to resolve that, we can use this information and the idea that remember that a unit vector is equal to cosine theta x, cosine theta y, 0, to balance these things out. And there's some examples in the book. and I'm not really going to spend time on it. So we have a question to summarize that even though Spiderman's momentum is not changing, neither speeding up nor slowing down, dp/dt is not zero, and that's not right. Spiderman's momentum is changing at this instant because the direction of his momentum is changing. So, and that's a key point. So at this instant, so dp/dt is not zero because his momentum is not, his momentum is changing. How do we know that his momentum is changing? Because the direction of momentum is changing. And the whole point of this dp/dt perpendicular that we're talking about here is that what this is the change in direction. So that's the component of dp/dt that talks about change in direction. Now, the magnitude of momentum may or may not be changing, but the direction of his momentum absolutely is changing. And so dp/dt is not zero because his momentum is changing, even though the magnitude is not changing at that specific instant. The direction absolutely is changing. And so dp/dt is non-zero. So that was an important question. Thank you.